will wait one moment that they erase the definition. So you have two star algebras, A1 and A2. And then you have the tensor product of these star algebras. Okay. And let us put it A. Then any star algebra, when I speak of algebra, remember, I always mean algebra associative and with identity over the complex. If some of this requirement is not required, I will be excluded. If I don't mention it, means complex algebra associative or with identity. So, given that since the algebra is identity, it makes sense to speak of the states of this algebra. Remember that the states are the positive linear functionals on the algebra, normalized so that the expectation of the identity is 1. Okay. So, and this among these states, this subset of states contains the tensor product states of these are state on A1, state on A2. So if phi is 1 is a state on the algebra A1 and phi2 is a state on algebra A2, you can form the tensor product. Okay. Yeah. So since it contains this product state, obviously the state is a complex set. So since it contains a set, it will contain the closure, the convex envelope, the convex hole of this. So so the S of A contains the convex of the product states.
Yes.
Okay. If we put a topology tau, T, let us call on A, we can speak of the closure of the convex in that topology, because any topology on A will induce a topology on the states. Yeah. Okay. So, and we take the continuous states. So, this is a topology. And then the definition is very simple. Definition. A state phi on A is called entangled if it belongs to SA certain radical difference with disclosure. So in finite dimension we don't need closure. algebra will be the matrix algebra on C2 tensor C2. And it is well known that this is the, this is the tensor product, but this is also the matrix, the bounded operator, the matrices over C2 tensors. Okay? Then you define the state phi A equal by definition psi A psi. For every A that belongs to this M2 tensor M2, which is isomorphic to the 4x4 matrix. Okay. And this is this state here, if psi is this form, the corresponding state of the matrix algebra given by this expression is called the maximally entangled state. Okay. So this is the definition of what is entangled. An entangled state is a state which cannot be approximated by linear combination of product states. So the definition is unique of entangled. And then you can, there are many definitions. Okay. In quantum information, they give a great importance to this notion of entanglement. Okay. Of course, mathematically is a nice problem. All problems that are related to convex sets are typically hard, and they are computationally hard. My personal opinion is that this notion is a little bit over-evaluated, this notion of entanglement. It is interesting, but it is not, in my opinion, the metaphysical content that it is attributed to it in the quantum information community.
So, I think there's another question I want to ask you. We have been introduced to interacting form spaces.
Yes.
Here works on the quantum stochastic differential equation that are defined on such IFS.
Yes. This was done in the thesis, but I want to say that the results are preliminary. There is a lot to be done. You will see the theory of stochastic integration in interacting form space. Of course, you are to speak of stochastic integration, you need notion of matrix, so you need a time situation. So you will need interacting form space of similar type as the Hudson-Baldassarrati. That is a kind of, if you call gamma omega, if you call gamma an interacting form space over H, this H cannot be arbitrary, but must be of the form L2 of R with values in a multiplicity space K. Because you need an index, a time index. Once you have the time index, you apply the general theory that Professor Lucas mentioned, representation free stochastic time. And then you can develop the theory of unitarity. The most important theorem is unitarity. And you can do it. Okay. There was a thesis many years ago, but the literature
equation, well, Professor Luca is mentioned in the general framework, but we can take advantage of the special structure of interacting flow to have an easier equation rather than the most general non-representation free stochastic calculus. When the theory is too general, it is difficult to find interesting examples. So in mathematics you always have to look to interesting cases, and this will be given by interacting flow. If you want, we will put the bibliography in our notes on this topic, so you can, and we can also send a file of this paper if you want. Okay.
So, another question. There is this work on Z2 gradient quantum-stochastic calculus.
Right, it's a fair.
And it's
Z2 gradient,
is
the
it not
thing is the
interesting
same.
because there are not so many literatures on it?
Not so much. Well, the first extension to stochastic calculus to Fermi case was done by a student of Professor Hudson, David Applebaum, who spent also after this thesis 1 year in Roma with me, and so this is the first result, and there are many results on. Of course, the literature in the Fermi case is less developed. The stochastic integration in the free case was first developed by Kummerer and Speicher, and exactly in the same year they came to the QP conference and explained this. And Professor Fagnola showed that our representation free calculus can include also the free calculus. Just what we did not, what he added to our calculus was the fact that you have to distinguish in the free case left stochastic indica and right. But we were using the raw computation relation, so we did not distinguish left and right. But if you make this distinction, then the free calculus is a particular thing. So that you can develop many calculus. But that is why we think that a representation free calculus is very necessary. Because the same is true in classical probability. And the classical probabilities don't develop one calculus for the gamma, one calculus for Wiener process, one calculus for the Poisson process. They have a general theory of the calculus for semi-magnitude. And this is what we did in the quantum case in the representation free calculus.
So, as he's talking, white noise for multidimensional cases. People to treat it as God mentioned it.
Well, I mentioned this, that in white noise we can have white all stochastic calculus. When you take the white noise approach, it becomes much easier to deal with the non-adaptive processes. But there is one result which unfortunately is very fundamental. But probably, well, there is a very long discussion about it. There is one result which in the multi-parameter case, multi-parameter means that instead of taking a stochastic process that is to a one-dimensional index like that you interpret as time, you associate a random variable. For example, WT, the Lutheranian motion at time. Okay. When you speak of multidimensional, usually we speak of random field. So you have, instead of T, you have X, which is an element of RD, and you associate WX, which is a random variable. So if you want to try, that many people try, but to do it using the martingale approach, the user in big troubles. But if you use the white noise permutation, it becomes very easy to do stochastical integral for non-adapted processes. And then you can do partial differential equations for non-adapted. Again, the stochastic integration was developed by us with Borovich and Leroux in 1999, but since we were so busy for other things, we could not develop the theory of partial differential equation. For example, Klein-Gordon, that would be the main fundamental example for non-adapted stochastic. To do stochastic Klein-Gordon using white noise. That would be an important research program for a very, very high level application, or for research publication.
White noise flows, free white noise flow. Free white noise flow. That was made in 2017.
Well, this is another side. When we were doing stochastic limit, again, we were motivated by physics. So when we were doing stochastic limit, we found that if you do stochastic limit for strongly nonlinear interaction, and the fundamental example, the first example was quantum electrodynamics. Then, mysteriously, this is really a mystery of mathematics, why this happened. I mean, we understand that this happened mathematically is a Riemann-Lebesgue effect. You know Riemann-Lebesgue lemma, that oscillations are killed asymptotically when you have large parameter in the yeah. So you have this Riemann-Lebesgue effect that kills oscillation, and the usual Feynman diagrams of quantum electrodynamics become the free diagram. This is very, very mysterious, but very interesting. And then we discovered, in the 10 years after, we discovered that this is not related only to QED, quantum electrodynamics, but this is universal for all strongly nonlinear interaction. Astrophysics interaction, Anderson model, stochastic Bosanization. This is a universal phenomenon. So we need white noise for free, but for free diagrams, not for the semicircle. Because the measure is very, very much more flat. But the diagrams are the free diagrams, non-crossing diagrams. You see, the Gaussian, I give you the example in 4 points. What do we mean by diagram? You see, if you have 4 points, and you have, these are the non-crossing diagrams. And these are, there is only one crossing diagram, which is this. In usual boson theory, all crossing and non-crossing. In free theory, only non-crossing. Okay? This will correspond to an expectation of this form. For example, vacuum expectation value of, say, four of a product of 4 of the X can be creator, annihilator, X1 is can be whatever. Okay. And the diagram corresponds to the pair partition. Essentially, is a form of Gaussianity, quantum Gaussianity. So you see, this is the free natural emerge naturally from physics. We don't know, for example, if monotone can emerge from central limit theorem, but we don't know if it comes from physics or not. We have not yet found an example in which the stochastic limit of something is monotone, for example.
Can you advise everyone to go on to white noise stochastic differential equation following these kind of approach which you did in 2005?
It was in the beginning. The first is the series of lecture notes in the Trento school, which is a school like this, but it was in 1999.
Sorry, that note, I could not get it.
Oh, I can give you.
Is that right?
Because there we did a systematic explanation
Yes.
of what does it mean stochastic integral with white noise stochastic. But then other people, I wrote several papers on the white noise together with the Dayer. And then also Professor Kuo wrote some paper on white noise, but from the classical point of view. We were using the quantum way. Professor Kuo used the classical. Hida way. This was after our work, because it was realized, in fact, it is a joint paper with Kuo and with the Dayer.
Any other questions?
Okay.
So before I ask the question, I want to ask if you can actually share that material that I wanted to show to everyone. Like maybe you can share with the public also. That material that you wanted to share, that's the
Okay,
Why
the
is
material.
that?
Well, it's not a problem. He wants the material that Professor Ezekiel is requesting.
The 22 school,
The school
1999.
material, in 1999. You
did
said you
this
can
one,
share.
okay.
You can do that, but you can't do that.
Just very specialized on white noise interactive space quadratic.
It's as if it's not
the information stored in the spoke about the research did on information stored on the quantum information, something like that. And when you ask the question that man told you to help me to answer.
The lecture is this morning.
Yes, and the other question
You
was
want to know this definition of the index of information complexity.
of the quantum and it's kind of linking both sides, both the question of the information of the quantum state and
Yes,
and
I
the entanglement. I usually hear that the information being transferred from during entanglement is meaningless.
No, this is another story.
Okay,
There are two
right.
different things. This morning I explained that using the probabilistic quantization, you can introduce an information complexity index for classical probabilization. Then there is what Professor Susi explained, that this was very much developed by my friend Professor Oya, that he introduced mutual quantum information. This mutual quantum information is probably the fundamental notion of quantum information. Quantum?
He's asking whether you mean quantum information is describing the basic state of quantum in the sense of method and.
No, I don't.
I know it's not from a physical point of view.
I don't understand the question.
Maybe he wants to understand quantum information from the perspective of a physicist, interpreting it from quantum mechanics background as position and momentum operator. Yeah, quantum information in that.
It's a little bit vague in this statement.
familiar with that. Am I right? Now he's coming to
With
see the
Professor
theoretical
Oya,
background.
we were the first to give the mathematical formalization of what is teleportation.
So you can see what is it.
And in fact, in our paper was proved that for teleportation, a maximal entanglement is a necessary condition. Then this condition has been very much taken in the literature, but the first paper was this one. If you want, again, I can send it to you, about quantum teleportation. Because Professor Oya and his group, they made the mathematical generalization, mathematical formulation. But the theory that for quantum teleportation you need maximal entanglement is in our paper.
That's that. Thank you.
Okay, any other question?
Yes, yes.
Okay.
Oh, okay, Prof. In this your definition of entanglement, you are applying to algebra. Maybe start algebra.
Yes, I did very qualitative. In general, of course, in practice it is applied in metrics actually.
In metric
99.99% of the literature concerns only matrix.
Oh,
Because in quantum information they only deal with the finite. Okay.
that settles my problem.
Yeah.
Other question? What will be the application of USC to biology?
Bioinformatics.
Bioinformatics.
Ah, well, you see, this was a big dream of my friend Professor Oya, who founded a laboratory of quantum bioinformatics. In fact, some of his students reached a very high level position in medical schools by applying the method of information and of statistics to, for example, DNA. This is but this requires that you are expert in computer books, not only in statistics and mathematics, but you have to know how to program, or at least how to put good questions to those who know how to program. So the biology, the quantum biology is a very old problem. I have a son that quantum effects in biology.
Cognitive sciences.
This is different, not biology. Cognitive is not yet. Unfortunately, we are not at the level of having reached a synthesis between cognitive science and biology. But there are many attempts in this direction. But I don't know how solid these attempts are from the point of view of the solidity of the knowledge. Many things are ideas. Ideas, of course, are very important, but then in science you have to give a concrete form to these ideas, otherwise it remains a word. Okay. So I think the opinion of biologists, with whom I have discussed it many times, the biologists have the opinion that the quantum effects are still too weak. And they involve too small distances to be experimentally detected with the experiments that biology now, with the technology that now is available to biology. They can, the quantum effect is not so, see, the quantum theory was born for the microscopic world. The attempts to go into a macroscopic world like biology means we are extrapolating the original physical domain of quantum effects. Okay. So we have to be very careful when we want to do something like this.
Okay, Prof, I
Prof,
want to
please let me ask Prof. Now, these concepts that you have just considered, can one extend these to groups?
Which concepts?
probabilistic quantization.
Quantization, entanglement, can one take them? Because you said it's only for finite dimension.
No.
So-
Entanglement, I gave, the definition is
Yeah.
general.
Yes.
I say the modern contemporary literature
Yes.
only considers finite dimension.
Finite dimension. Yes.
You see, but is a sociological reality.
Yes.
It's not a scientific. You can also do in infinite dimension. The problem of group is, you see, the notion is what do you mean? For example, you can look at group theory from many points of view. For example, you can look at the rotation group, and then you have rotational sphere, and you have the orthogonal polynomial sphere, and so you can apply the theory that we are describing in these lectures to the particular case of orthogonal polynomial on the sphere, Bessel. See, and Bessel function. And in fact, the Bessel function appear in, for example, in the example I explained this morning. Bessel functions are very important to express the solution of Schrödinger equations for the free Hamiltonian in the arc sign and the semicircular quantum.
Arc sign.
Yeah. So you can do, but this is a very nice mathematics, hard mathematics.
Yes.
That's the particular.
Likewise, in line of the question of Dr. Ezekiel, I'm just thinking, the quantum calculus, can we also extend it to time scale calculus?
Time scale.
Calculus.
What do you mean time scale calculus in this field? What is time scale calculus? I don't know.
There's a calculus named time scale. I read it in the literature. Of the delta differential calculus. They also call it the delta differential calculus. It's relatively new anyway. It's relatively new.
Time scale is not so new. I think it has been done.
self-similar fields and stochastic process. Self-similar stochastic process is one of the very fundamental notions in classical probability. So, of course, we can do the extension to quantum, provided that the condition of all moments is satisfied. Okay? But I understand time calculus, time scale calculus is not clear to me. If time scale means invariance or quasi-invariance of a process under time rescaling, this is a very famous notion, a very famous topic in classical probability. In quantum there is not so much rich literature, you see. But there exist some examples, but not so much developed. This would be very interesting to develop.
Thank you. Well, let me ask you a question on applications. I have seen so much work that is done by John Goff and his collaborators. Okay. I've also seen so many work done by Esatar in France by his collaborators.
Who?
Esatar.
Steven Attar.
Stefan Attar in France.
But this is not on application.
Yeah, some of them they develop mass application in order and optics. They use in optics.
No, but they are phenomenal. I know that, you see, what Attal did is the following thing. You remember that I explained the story of the Bernoulli central limit theorem that was discussed by Professor Lu in the first lecture. That there was the era of quantum probability in Rome, and Passarati and Lindsay developed a way to approximate quantum Brownian motion in a similar way as we had done before with Bach, Alexander Bach. What Attal did is to take this result of Lindsay and Baltasarati and try to give a phenomenological interpretation for quantum optics. But the phenomenological is not true physics, because in stochastic limit we start from the law of physics and we deduce the stochastic equation. Attal was beginning with the phenomenological stochastic. So you put by hands the parameter that we deduce from physics is stochastic limit. You understand? So I don't consider this a deep theory, because you find what you have put by hands at the beginning. You see, because you put the parameters of the quantum Brownian motion in the beginning, the approximation. And stochastic limit is a much deeper physical theory, because you start and you have the microscopic structure of the parameter as a function of the Hamiltonian, the microscopic Hamiltonian. So you really have applications. In fact, control theory was what we call physical control theory. We have many papers on this with Imafuku, a Japanese who spent many years in World Tour with me, and we make a kind of revolutionary proposal, because in physics, if you look at the literature in control theory, they say that the main problem is to avoid the coherence. Okay? However, we, in stochastic limit, we had examples of exponential decay to equilibrium. And so we argued as follows. Suppose that I prepare a physical introduction. That is why you need stochastic limit. And phenomenological model like Attal cannot work. Because you need the meaning of the microscopic parameters. So, if I can bring a quantum, starting from a quantum state, I can devise an interaction such that it is decoherent because it decays, but it decays to a state to which doesn't mean decoherence. Many physicists believe that decoherence means that the state that you reach is not pure. It's not true. We have a lot of examples in real quantum optics, not mathematical quantum optics, of decoherence which converge to a pure quantum state. You see? And so we say if we can take a state at time zero and in exponentially short time bring it to another state, we are controlling the state. It's very natural.
Yeah, and that follows the interpretation of controllability.
Yeah.
True sense of
Yeah.
the meaning.
And this line was then continued by my student patient with an important American mathematical physicist in Princeton, rabbits. Patient and rabbits developed this we call control through decoherence. And they call decoherent control. It's the same thing, but the idea is that one patient learns from us. You see?
So is that why the control of the by Belafkin just
The Beliavkin, there is, if you look in my book of my book with Molovich and Lou, there is a chapter devoted to Beliavkin quantum physics. And we express how to look and to combine it with the stochastic group. So that if you are interested in control next year, the QP47 will be in Monastir in Tunisia, and it will be exactly dedicated to put together community of control, also classical, and quantum probability. So quantum control will have a very big role next conference, next QP47 will be important for quantum calculus.
But Prof, they have not accepted our definition of quantum stochastic differential equations, the way the control is being initiated. Because he was trying to represent this yesterday with Lucas, and he was referring back to us, and he was referring back to him. He reviewed some of his papers.
Now, can you repeat? I have not answered. You
Yes.
produce a quantum control logical.
Yes, in quantum stochastic differential equations, the beauty of it is the factor of control that is added, and that makes it a set rather than one component that we use. Okay, and that is the basis of formulation by Canberra, which we have also followed over the years. All we're saying is, like we are arguing today, that most of our publications, when we send them out, they seem not to want to, accept what we do. Yeah, because so we wonder why, because in control, the major part that has been established in the quantum field. So this is the confusion. Even if they would accept these papers, they seem not to want to, see the object that is being defined in the construct. So we see it as a challenge to us, which is part of the world, our kind
So
of.
you want to apply your inclusion theory of stochastic inclusion to quantum control.
Yes.
Yes, I know.
We believe it is more robust.
Okay.
But
When it does set value.
yeah, when it's set value,
It's set value, it's bigger.
it's bigger.
Yeah.
Yes. So maybe next year, I hope more of us will be able to attend.
You can present some
Some of this is not
try some result on this direction and to discuss with experts of quantum control. I am not expert of quantum.
Yeah, I know.
I wrote a little bit on this chapter in the book because I was very good friend of Beliavkin and we worked together. And we also wrote this paper of quantum Kalman filter was out of discussion with Beliavkin. Yeah.
But John Goff also did control.
John Goff was
And he was using the representation that you established.
right. He spent 2 years in Rome. Yeah.
Yes.
John Goff, then I have Alberto Bertelli, who was also working in quantum optics.
John Goff actually used this
This
time. John Paul actually used TCP, time consecutive processes, to do its own explanation, application of quantum